Thank you all for attending, for lending me your ear and inviting me to your department. I hope I pique your interest and hopefully we can collaborate in the future. So as Alex said, I'm Ahmad Nemer, I'm a postdoc fellow at NYU. And today I'm going to talk to you about, I'm going to just take a deeper dive into the BPT diagrams and dive a little bit more into the liner emission, explain some characteristics of that emission. But before talking about the BPT diagrams, I just want to have one slide just telling you about my general interest. I'm really interested in modeling spectra. I'm interested in all the processes that are responsible for this line formation, including photoexcitation, photoionization, collisions, radiative transitions, and such. All the way down from calculating those rates into putting them all together in one model and producing a synthetic spectra that we can compare with actual observations. My work includes some of machine learning for post-processing, for inference, and in the case of today, for classification. The type of systems that I study, I'm interested in, goes all the way from hundreds of AU scales, such as protoplanetary disks, and larger to supernovae, planetary nebulae, H2 regions, and finally, galactic spectra, which is the topic of today. So, we are interested in classifying galactic spectra. So we decide on a target and then we obtain an optical spectrum. Of course, everyone knows that optical spectra are the most abundant because of ground-based instruments that are abundant. So it's the easiest to obtain. And we want to use this tool, the optical spectra of galaxies, to be able to classify them based on their dominant ionizing source, right? These can be broken down into two main categories. One is AGN. AGN are galaxies that have a supermassive black hole at the center that is actively accreting material. There's an accretion disk around it. The conditions in that accretion disk are exotic. And the interaction between the gas and dust and the AGN itself produces an X-ray radiation or a hard radiation. So when I say hard radiation versus soft radiation, it's just related to the energy of the photons being produced, right? The higher the energy, the harder the ionizing spectrum. It's not about the amount of photons being produced, right? So X-ray is hard radiation. On the flip side, we have galaxies that their supermassive black holes at the center are not actively accreting anymore. And the majority of the ionizing radiation comes from young massive stars. Those have a characteristic blue color because their ionizing radiation is a soft radiation, means it peaks at far ultraviolet and at the bluer part of the spectrum, hence the blue color, right? So how do we do that? Traditionally, the gold standard is the BPT diagram. It stands for Baldwin, Phillips, and Tillerich. Where in the 80s they calibrated known systems like known AGN targets and known star-forming galaxies. And they wanted to see if they correlate with line ratios and basically if they plotted those targets on these different diagrams, would they show us any kind of patterns that we can use to classify those targets. As I mentioned earlier, hard versus soft sources. So when you have hard sources, higher energy, higher ionization level in the gas, you'd expect higher ionization lines such as the S2, N2, and O3 lines to be more abundant, right? Those are forbidden emission lines. So they would occupy the top right corner of these diagrams, right? Because you'd expect those forbidden emission line fluxes to be higher relative to the hydrogen recombination lines. So in total, we have 4 forbidden emission lines and 2 hydrogen recombination lines. And the interplay between the two is something that we can use. Whereas for soft sources, you'd expect the ionization level in the gas to be lower. So you'd expect the hydrogen recombination lines to be stronger relative to the forbidden emission lines. Hence, those targets would occupy the bottom left corner of those diagrams. Further segregation or grouping was found. Like as you can see, we drew some boundaries here, and we have different colors, which I would explain in a minute. But those boundaries were mostly inferred through empirical analysis, right? So they collected a large sample of targets, and they plotted them against these diagrams, and they looked at different groupings within those larger populations. For example, I'm just going to explain this one diagram here, which is the most important diagram people use. As you can see, there are two wings of this, like this is a population of hundreds of thousands of galaxies. As you can see, there's a wing, and there's another wing coming out here. After some theoretical modeling that supports these diagrams, it was found that this wing is related to star-forming galaxies. Any theoretical modeling of star-forming galaxies could not produce any data points above this one line, for example. So it was inferred that beneath this line, it's probably a star-forming galaxies. Anything above, it's an AGN. And then further boundaries were drawn based on further analysis and larger sample sizes. The final classifications are the blue color in any of these diagrams is representative of star-forming galaxies. The red one is representative of AGN or Seyfert type 2 galaxies, whereas this black region here is something that is a bit confusing. It's called composite. It's not really well understood, but it's thought to be galaxies that have both AGN and star forming. So you'd get some kind of a mixing sequence here. Whereas the green color, which is the topic of today, it was classified as LINER, which I would explain in a minute. So what are these LINERs? LINER stands for low ionization nuclear emission region. So traditionally, these observations of galaxies were done with single aperture instruments, where the aperture covers the nuclear region of the galaxy, and the flux of those lines is just the integration of the line from this whole region that's covered by the aperture, right? So it's just a collection of many regions within the galaxy, right? Liners produce line ratios that are typical of hard SEDs, similar to AGN, right? So they occupy the top right corner. But the differences between LINER emission and Seyfert emission is that the luminosity of the LINER sources are lower, and that lower ionization lines within the forbidden lines, like the S2 is lower ionization than O3, and it was found that the lower ionization lines are stronger than the higher ones, right? So these two characteristics of this LINER emission made it a separate group. So since this was done in a nuclear aperture, or basically integration flux from the nuclear region, people used other instruments to try to find out what's going on in this nuclear region. So specifically in the LINER targets, we found that there's X-ray and radio in the nuclear region, in addition to the Balmer double peak, broad double peak emission. Those are all indications of AGN activity within the galaxy. So since we have hard SEDs, they occupy similar regions in the BPT diagrams, nuclear region, we have some characters of an AGN activity, it was thought that this is just a low luminosity end of the AGN sequence, right? So high luminosity AGN, low luminosity AGN, they group differently. One of the ideas was that instead of the AGN being directly responsible for line emission, it's a secondary, because it's a low luminosity AGN, it does not produce line emission in a similar case as a strong one, but maybe a secondary effect of this AGN activity, such as outflows and shocks, could excite this line, but still it would be connected to an AGN activity. So that was all done in single aperture observations. But more recently, we have IFU, or spatially resolved observations of spectra, where we can obtain spectra from different regions rather than just integrating the flux within the aperture that we observed it with. And this is one example from Melchoir's paper of one galaxy. As you can see, so the red presents AGN, blue star forming, and yellow is LINER. And this configuration of different classes within the same galaxy is not really consistent with whatever we thought about the LINER and AGN, because you have AGN activity not really at the center, really extended a little bit, but you also have LINER at the same time, and none of them is dominant in the nuclear region. So further evidence was provided that this LINER emission could be actually due to post-AGB stars. Those are low mass evolved stars. And I'm going to talk about this point later on in more detail. So all that is just an introduction about the problem. My part. So my idea was that we've been relying on strong emission lines to classify those spectra, but what about the information contained in the rest of the spectrum, right? Other than outside of those strong emission lines. Like you'd expect dust to affect the continuum, and that would affect the slope of the continuum of the spectrum. Maybe the shapes, broad versus narrow emission lines. Those could be things that we can use to classify the spectra in addition or in support with, to the BPT diagram. So for this purpose, I used Spender, which is an autoencoder, a neural network-based autoencoder, which was designed by my colleague Peter Melchoir in 2023. The initial purpose of this autoencoder was to reconstruct specifically SDSS spectra. And that's what I'm using for this project, SDSS spectra. The way it works, just briefly, I'm just showing you here the encoder. So the autoencoder is comprised of an encoder and a decoder. So I'm just showing you the encoder part of the autoencoder. And there's a decoder part here, which I'm not showing. So the way it goes is that you feed the spectrum. It has something like around 4,000 spectral elements. So it's a very high dimensional manifold, which you would like to reduce into a lower dimensional manifold or a latent space or data summary. So you feed the spectrum, it passes through 3 convolutional blocks with varying kernel sizes. The purpose of this convolutional blocks is to scan the spectrum and detect important features. And there's an attention layer. So this attention layer takes the information from the convolutional blocks, and points out to the parts of the spectrum where that contains important information needed to identify or uniquely identify these spectra, right? And then it goes into an MLP, and then eventually you have a latent space that is representative of the full spectrum, but with a lower dimension. And then the decoder part, which I'm not using for this project, takes this latent space and then blows it back up to the higher dimensional space. It reconstructs the full spectrum, but you can play with the sampling rate and noise and such things. So instead of using the encoder as a data summary instrument, I'm using it as a classifier. So the latent space is just made up of one variable, and that variable is a label. It's either a 0, which means it's a star-forming, or this is a spectrum that belongs to a star-forming galaxy. If it's a 1, it's a Seyfert. If it's 2, it's a liner. So I'm showing you two samples of spectra that I used. This spectrum is basically the full spectrum. You can see there are emission lines, and you can see the continuum. And I did the same experiment with the same spectra, but I masked or subtracted the strong emission lines. So this is not the same spectrum, but a similar spectrum, but this one is with all the strong emission lines being subtracted. So as you can see, what we can see here is just the continuum. The continuum really is a result of the underlying stellar population that is observed within that fiber. So this really traces the stellar population and can tell us something about the age, the metallicity, and the characteristics of the stellar population that could produce this continuum. So some statistics just to explain the experiment. I'm relying on the SDSS-MaNGA database, which is a database of 10,000 galaxies, 10,000 data cubes. Each data cube has many spaxels covering different regions within the galaxy. The total number of spaxels is something like 3 million spaxels, but I wanted to filter out low quality data. So I used a signal to noise ratio for all the strong lines that I'm using in the BPT diagrams of 5 and above, which would reduce the total number of spaxels to something like 1.2 million spaxels. Out of those, relying on the BPT diagram classifications, the majority, like 75% of them are star forming, only 2% are Seyferts and liners, and the rest are what we call ambiguous classification, because they're classified as one thing in one of the BPT diagrams and classified as something else in another BPT diagram. So it's kind of an unsure classification, so we just filter them out. I use an equal weighted sample of each one of those categories, something like 20,000 spaxels, and I split them into a training sample and a testing sample. So for the training sample, I use the BPT classifications. I label those spectra 0, 1, or 2, and then I start training the encoder. Basically, if you see this spectrum, it means that it belongs to this class. So I can explain more about the training routine later on, but we went through the training, and then we used the remaining sample of 15% just for testing to see if we feed spectra that the neural network has never seen, would it be able to correctly classify them consistent with the BPT classifications. So using the first one, which is in which we use the full spectrum, including the emission lines, we found that the neural network was able to correctly classify or correctly detect each one of those classes with a high fidelity, right? Like 99%, 95%, 96%. So I did the same experiment, but now I'm just feeding the spender the best fit continuum model, subtracting all the strong emission lines. And the detection rates are, as you can see, for star forming, it's almost the same, but for liners and Seyferts are reduced. So let's just take a minute and see and try to understand what this means. So for star-forming spaxels or star-forming spectra, whether you use strong emission lines or you use the continuum, which contains the information about the stellar population, you can still get a very high detection rate, which means those spectra can be distinguished either by their strong emission lines or by their stellar absorption features. And that is something that is reasonable, because we know that star-forming spaxels are excited due to young massive stars. And those young massive stars would leave their signature either in their strong emission lines or in their absorption features. Please.
Right. But are these spectra flux calibrated? Or?
Yeah, those are like DAP, so the data analysis pipeline.
But the information is coming from the absorption lines, or is it the shape of the SED?
So,
or is it both? When you talk about this, that it's still succeeding to classify.
Right. So maybe I neglected to mention this point. So this attention layer can tell us which parts of the spectrum are important. So when I looked at the full spectra, the majority of the weights in this attention layer are focused on this part of the spectrum where you expect the strong emission lines. But there's a little bit of emphasis on this blue part of the spectrum, around 4,000 angstroms. But when you remove the strong emission lines, all the weights and all the attention is focused on these absorption lines. So it seems that these absorption lines are what is needed to distinguish these spectra. It is a surprising result, because I expect maybe the slope, maybe the shape of those lines. It turns out no, it's actually the absorption lines that matters. So back to this point. So for star-forming spaxels, you can either rely on the strong emission lines or the absorption features to distinguish these spectra. But for Seyferts and liners, because it was thought to be due to AGN activity, you'd expect the strong emission lines to have the signature of these two classes, but the continuum itself should not, because it's just related to the stars, and the stars are allegedly not responsible for line emission. But this result is actually surprising. There's a group, an actual large group of liner emission that can be distinguished just by their absorption features without relying on their strong emission lines. So there's some connection between the stellar population of these spectra and line emission. And this is something we're going to investigate more. So from this point on, I'm just going to focus on three groups and analyze them further. I'm going to look at the liners that were detected only using their absorption features to see what is the relationship between the stellar population and the line emission in this group. And then there's this group of liners that were distinguished using their full spectrum. But this includes both liners that can be distinguished using their strong lines and their absorption features. So this sample is called best fit liners, or BF. This group is spec minus BF. So I subtracted this group from this group just to focus on the ones that need the strong emission lines to be identified. And then the third group is the star-forming group, because we can learn some things by comparing the other two groups to the star-forming group, and I'll explain that in a minute. So what things can we tell about these spectra? Absorption features of stellar population can be characterized through their Lick indices. Lick Observatory, some 30 or 40 years ago, they cataloged spectral indices tracing those absorption features that we can use to either infer metallicity or the age of the underlying stellar population. For example, this D4000 break index, it's a well-known spectral index that traces the age of the stellar population. The higher the index, the older the stellar population is. And as you can see, the BF sample has the oldest population, and the SF sample has the youngest population. Another two spectral indices, the iron and magnesium lines, these are used to infer the metallicity of the underlying stellar population and the enhancement of alpha elements also within that population. And as you can see, similar thing. For the BF sample, in both cases, they have the highest enhancement in metallicity in their stellar population compared to the star-forming one. Lastly, this H delta F, it's a higher order Balmer line. Mainly it's used to infer a most recent star-forming episode within the galaxy. So the higher this value is, the more recent star formation episode has occurred in that galaxy. Again, similarly, for star forming, because it's a star forming region, you'd expect star formation to be ongoing or just very, very recent. So it has the highest value. Whereas for the BF sample, almost centered around zero, close to zero, which means there is no recent star formation activity going on. I'll group all these conclusions later on in the slide and explain what they mean. Furthermore, the nice people of the SDSS developers, they basically provided general properties of any of these spaxels based on rigorous spectral fitting, where they try to infer the stellar population continuum and the parameters of the stellar population. So I'm just picking some of the information that we can use in our analysis. For example, here we have the light-weighted age of the stellar population. And this is in log age, or log year, basically. For the BF sample, age of the stellar population is in the tens of the giga-year. So it's a pretty much old stellar population. Old evolved low-mass stars, probably, because if they have higher masses, probably they wouldn't survive that long. They explode much sooner. Whereas in the star-forming sample, the stellar population peaks at hundreds of millions of years, which is what you would expect from young massive stars, because they wouldn't survive longer than that. So older population, younger population, expected. Another thing is the elliptical coordinates of the spaxel that we're observing, and this is in units of R effective, half-light radius of the galaxy. So this was a surprising result, because it was thought that if you observe a nuclear liner emission, that probably belongs to low luminosity AGN. But if you observe extended liner emission, that probably is due to either shocks or post-AGB stars. Whereas what we found here is the majority of both samples, BF and spec minus BF, are concentrated within less than a half R effective, which means they're pretty compact in the nuclear region. And this is also something that makes sense, because you'd expect all the evolved mass stars, low mass stars, to be in the bulge. So you'd expect them to be concentrated mostly in the center. Whereas for star-forming ones, they're just all over the place. They can be either too close or extended within the galaxy. H alpha equivalent width is something that people use to be able to infer the strength of the AGN activity. Usually if you have an equivalent width of 6 and above, that's a strong AGN galaxy. Anything between 3 and 6, that's a weak AGN activity. And anything below 3, it's what is called fake AGN or retired galaxies, where basically there's no AGN really activity, but so that's why it's called fake. And as you can see, for the BF sample, the majority of the spaxels actually are less than 3, which means they're not really AGN. Whereas for the spec minus BF, actually they peak around 4, which means they're probably AGN, but weak AGN. So there's a clear distinction between these two classes just based on the equivalent width of H alpha. Lastly, just looking at the metallicity of the stellar population and the metallicity of the gas, the emitting gas of these lines. As you can see, for the BF sample, the metallicity is enhanced in both cases. And that's a significant finding, and I'll explain that why. So our conclusions based on previous findings and today's findings as well are summarized in this slide. What excites liner? So it was known that liners are found in galaxies of earlier type, and that their continuum are dominated by old stars. That's something that's been known since the 80s. But also it is known that AGN are more prominent in retired galaxies. So it was thought that this is just a result of AGN being found more likely in retired galaxies. So Kaufman, 2003, it's a very famous and important, impactful paper. Because liners were found in earlier type galaxies, and because liners have some resemblance to AGN spaxels through the hard SED that produces the line ratios, through the X-ray and radio and such, it was thought that both belong to AGN, and so they belong to earlier type galaxies, but it's probably classified as AGN. And this is something that we found in the previous slides that I showed you. The liner spaxels are consistent with earlier type galaxies, and something in the tens of the giga years. But more recently, for example, Stasinska found that although liners do come from earlier type galaxies, those galaxies are ret sequence, or they're retired, or they're passive, means there's not much activity going on with the star formation or AGN. And this is something also we confirmed with the H alpha equivalent width, that the majority of the liners are actually fake AGN, not even weak AGN, which means that they are retired or passive galaxies. So this is kind of a strong evidence that it's unlikely to be AGN and most likely to be consistent with post-AGB stars. Lastly, Yan and Blanton, they studied the strong line emission ratios that we use in the BPT diagrams as a function of radius, and they looked at their gradients. And they created like kind of a rudimentary toy models to see if this gradient of line ratios can be produced from centralized sources versus radially distributed sources. And what they found is that centralized sources cannot produce this observed gradient in a large sample of galaxies. And more likely, it's probably a radially distributed source, and the distribution of this source resembles the distribution of stars within the galaxy. One last piece of evidence, there's a bunch of people in the department here that are really focused on post-AGB, and they study their characteristics, so you probably guys know better. But as far as I know, these systems are really hard to model because they're complicated, and there's a lot of uncertainties, and there's very few observations of such systems that we can constrain the models with. But more recent models were able to prove that post-AGB stars have enough photons, and those photons are hard enough to produce the liner emission. But the trick is that the source plus the supply of gas around it that would basically produce or basically produce these lines has to be either enhanced in abundances and or to have higher ionization parameter, or the gas has to be closer to the source than is typical of normal H2 regions, for example, right? So what does that mean? That's something that we already found here, right? We found that BF sample has a higher abundance, higher metallicities in their stellar population, but also has higher metallicity in the gas itself. And that's kind of the hardest proof for the post-AGB theory. Lastly, I'm just going to summarize my findings and talk about future work that we can follow up. This work has provided further proof that liner emission is not related to weak AGN, rather it's related to an old evolved mass star stellar population. The implications of these findings, if they hold true, is that we overestimated the AGN population in the universe because we counted both AGN and liners as AGN. So if liners turned out to be non-AGN, so we have an overestimate of the AGN population in the universe, and that affects the cosmological models and our understanding of how the universe evolved. Another thing is that, as I mentioned, there's very few observations of low mass evolved stars. This this work really opens up a new window where we can probe and constrain and observe these systems and hopefully basically better come up with better models to describe them based on those new findings. This work needs, to be more conclusive, this work needs more follow-up where we target known evolved post-AGB systems and hopefully probe the gas around it and try to see the interaction between the evolved mass, low mass evolved star and the gas around it. Because these systems, the post-AGB stars, they're known in their just the most recent episodes that they eject their outer envelopes, and those outer envelopes are enriched in metals because of the nucleosynthesis processes that happened in the post-AGB stars. So you'd expect those envelopes to be enhanced in metallicities, and if they were ejected and didn't really travel that far away from the system, for it to be still connected to it both kinematically and radiatively. And that's something needs to be confirmed with observations. Lastly, this study was done with the SDSS-MaNGA database, and the MaNGA database is really focused on low redshift galaxies within a certain slice. I think it's something 0.05. Whereas I think those conclusions could be different or might hold true for higher redshift galaxies, because in the early universe, things worked out differently, and the enrichment and basically the processes that will produce those post-AGB stars might not be possible at that redshift. And that's about it for today. Thank you so much for listening. I hope you enjoyed the talk, and I'd be happy to take any questions.
So you're going to study higher redshift. I'm sorry if you mentioned this, but what is your current sort of redshift?
I'm not sure the MaNGA. It's like a very narrow slice in the redshift. I think it's somewhere between 0.01 and 0.05. Right. Yeah, so it's pretty close.
So initially, when you had the plot, of the galaxy, what's like the spatial resolution that you can see?
Kiloparsecs, really. So in previous observations, single aperture observations, the resolution, spatial resolution is in the kiloparsecs. So you cannot really resolve any of the important features. But for the IFU, depending on the distance of the galaxy, we can go down to like a few parsecs, maybe 100 parsecs, which is enough to really distinguish between the bulge and disk.
Is there any hope to actually see the disk structure inside of the AGN disk, or is it hopeless?
It's not really hopeless. So the newer version of SDSS is the SS-V. There's local volume mapper, where they will go down to few parsec spatial resolution, but they can only do that for local galaxies like SMC, LMC, maybe M82 and things like that. Hopefully, if this works out and we can convince people to fund such a thing even more, then we can extend it to higher redshift.
The idea is that these liners have a large population of post-AGB stars,
right?
And these other SF and the Sigma do not have this, right?
They might have it. It's just that whatever the stellar population in these spaxels are, they're not really responsible for line excitation. So like for the Seyfert type, it's the AGN radiation source that is responsible for the excitation. So the stars around it do produce an ionizing source, but it really doesn't dominate over the AGN.
I guess my question was going to be, these liners impart some weird absorption lines in the spectra that could be used to distinguish them from these other objects if they didn't have post-AGB stars. Because you mentioned that, they're ejecting a lot of these weird metals, right?
Right.
So that could affect the spectra. Or is that correct?
Right, that's correct. So when we talk about stellar populations, there's probably a large range of stellar ages, but what we care about is the dominant stellar population within this stellar population. So you might have something like 10% young massive stars, 20% main sequence stars, but the 70% is post-AGB. Whereas in the star-forming spaxels, the majority, like something like 80-90%, is just young massive stars that haven't evolved really to the giga-year.
Nice question about the BPT diagrams in general, but these are equivalent width ratios, right? That you see. So doesn't composition anomalous a bit, or because these galaxies could have different oxygen abundances or sulfur abundances.
So, again, based on very rudimentary theoretical modeling, we found, for example, like this sequence that represents star formation is dependent on two extra parameters, the metallicity and the ionization parameter. So higher metallicity ones would be in this sequence, whereas the lower metallicity ones are here. But still, it could never go beyond this boundary here. So it does depend on other parameters that we're not considering, but at least we know in the general region in the BPT diagrams where they belong.
So, if these are post-HEB, is this a very short-lived phase of galaxy evolution? Is that much?
So that's a very good question. So it is really not known when does this stellar population transition from the AGB phase into the planetary nebulae phase and then eventually into the post-AGB phase. But because those are low mass, so based on the modeling, we'd expect those to have 1 to 2 solar masses. So they're pretty low mass. So these can survive much longer. But how long would they survive and how long do they stay in that phase is something that we need to follow up with observations. But you're right, like higher ones, like 3, 4, 5 solar masses, they wouldn't live longer than a few thousand years. It's not enough for us to observe. I think what was found is that they live longer, yeah. So I'm happy to refer you to this paper. It was done by the group of Charlie Conway, who has a very sophisticated stellar synthesis model, where they found that it has to be specifically between 1 to 2 solar masses. Anything higher and lower would not provide the UV flux intended. So the core helium burning stars, I think, I'm not really an expert in stellar synthesis, but I think they have higher masses, and I'm not sure about their metallicities, but there's a specific range of age and metallicity of the stellar population that can produce the UV flux. Right, exactly. Yeah, it could be high metallicity.